Alright, what is up everyone? This is going to be my solution to problem C from LATOKEN round 1. So, as always, I'm going to assume you've read the problem already, so I'm just going to get right into it. So, I think the samples from this problem actually give a really good idea as to what the solution is, so I'll just work through the samples. So, in the second test case of a first sample, we have the first array looking like 2, 6, 5, 1, 4, 3, 7, 8. And the second array looks something like 3, 8, 7, 5, 1, 2, 4, 6. So, the way that they give you this input is they give it to you as like 2 arrays. But the thing is that one operation consists of like essentially swapping like same numbers, the numbers in the same column. So it's actually not super helpful to think of the problem as like you're given 2 arrays. I think it's better to think of it as you're given n pairs. So instead of thinking of it like this, let's try to think of a problem like this. So if we have like 2, 3 over here, we have 6, 8 over here, 5, 7 over here, 1, 5 over here, 4, 1 over here, 3, 2 over here, I guess 7, 4 over here, and then the last one I'm running out of room, but it's 8 and 6. Yeah. So this is like a better way to think of this problem. So let's try to make some observations about this. So 2 and 3, let's assume we can either put it as like 2, 3 or 3, 2. We have essentially 2 options for this first pair. Depending on what this pair is, it uniquely determines what this pair is going to be. And the reason why is that if the 2 is put in this first row, then the 2 in here has to belong in the second row. And because we're guaranteed that both of these numbers are permutations, each number will occur exactly twice. And that's really important. Because then we could say like this 2 to 3 will force, if we put this 2 on the top over here, this 2 is forced to be on the bottom. And so there's exactly 2 ways to configure these 2 pairs together. And a similar logic applies for 3, but because they're the same pair, it cancels itself out. It doesn't really matter. So, and the same thing applies to 6, 8, and 8, 6. This essentially forms like another group, because if the 6 is on the first row, the 6 has to be on the second row. If the 6 is on the second row, the 6 has to be on the first row. Same thing. But let's look at the remaining pairs. So let's start with 5 and 7. Let's assume that 5 and 7, in this 5, 7 pair, 5 is put on this top row. If 5 is on the top row, if 5 and 7 is like this, then we first want to look at the pairs with, let's first look at the pair with 5. So in this case, it's 1 and 5. Because 5 is on the top row, in this pair, 5 has to belong on the bottom row. So it's 1 and 5. Now let's look at this pair with 1 on it. If 1 is on the top row, then that means this 1 has to be on the bottom row. So it's like 4 and 1. And then same thing applies here. If 4 is on the top row, then we look at this pair and 7 has to be on the bottom row. No, 4 has to be on the bottom row, my bad. And then over here, 7 is on the top row. This means the 7 in the other pair has to be on the bottom row, in which case it already is. So what does this imply? Well, this implies that these common numbers give like a connection between 2 pairs, in the sense that if any 2 pairs are connected, then the configuration of one pair will uniquely determine the configuration of the other pair. So what I mean by this is that if we configure this pair over here, these orientations are the only possible orientations for these pairs. And if we flip this pair so that 7 is on top and 5 is on bottom, we have to flip all of these pairs in the same way to fix the solution. So now the question essentially becomes, if we were to group these pairs like this, we want to count how many components exist in this like collection of pairs? And the answer is simply 2 to the number of components that exist. So how do we find these components in the first place? Well, the problem actually like implies that you want to turn this into some sort of graph, because graphs components, that's just something that you associate graphs with. So what's really nice about this is that you can actually think of every pair in this like collection of pairs as an edge between two nodes. So for example, this pair over here, 1 to 5, we can think of it as an edge that connects 1 and 5. So what I mean by that, I'm going to draw that out really quickly down here. Okay, so if we have, actually I think I'll just label 1, 2, 3, 4, 5, 6, 7, 8. I think this is a little bit better. So let's start over here. We have a pair of 2 to 3, so we draw an edge from 2 to 3, like an undirected edge. 6 and 8, we draw an edge from 6 to 8. 5 and 7, we draw an edge from 5 to 7. 1 to 5, we draw an edge from 1 to 5. 4, we draw an edge from 1 to 4. 3, 2, we draw essentially another edge from here. 7 to 4, we draw an edge from here to here. And then 8 to 6, we draw like another edge over here. So 2 and 3 is its own component. 8 and 6 is its own component. And then we notice that 1, 4, 5, 7 also forms like its own component. So we have 3 components in here, which means the answer is 2 to the power 3, which is equal to 8. So the way that you can find these components is you can either use a DFS to count like how many DFSs it takes to visit all the nodes in this graph, or we can use a union find. Both work equally as well in my opinion. It doesn't really matter what you use, it's just about like what you prefer, honestly. Or I guess you could even use it like DFS/BFS, because in my code I actually use a BFS. But yeah, that's the solution to problem C. If you have any questions, leave them down in the comments and I'll try my best to get to them. Peace.